Look around at the sky on a clear night. You see maybe 3,000 stars. Feels like a lot, doesn't it? Well, those 3,000 stars are a joke. They're a thin little neighborhood, a handful of sand on a beach that stretches further than you could walk in 100 lifetimes. The actual number of stars in the observable universe is something like 200 billion trillion. That's a 2 followed by 23 zeros, and most of those stars have planets. So when somebody says, surely there must be other intelligent life out there, you nod. Of course there is. The numbers make it obvious that's completely wrong. And I can show you why. See, the mistake people make is they look at big numbers and assume big numbers automatically produce big results. They hear 200 billion trillion stars, and their brain says, well, with that many tries, something interesting has to happen. It's the same reasoning a man uses when he walks into a casino with $100 and says, surely I'll win something. Maybe. But the house always knows something you don't, and the universe is the house. Let me start where the confidence comes from, because the confidence is real. It's earned, it's just wrong. You've got a galaxy, our galaxy, the Milky Way, with roughly 300 billion stars. Somewhere between 1 and 4 billion of those stars are roughly the same temperature and size as our sun. A good fraction of those have rocky planets sitting at a comfortable distance. Not too hot, not too cold. We call this the habitable zone, and it's a real thing. Water can be liquid there, chemistry can get complicated. The ingredients for life are everywhere. Carbon, hydrogen, nitrogen, oxygen. These are not rare, they're among the most common elements in the cosmos. You find amino acids in meteorites that have been drifting through empty space for billions of years. The raw material is scattered around like confetti after a parade. And this is not just theoretical. Every time we point a better telescope at a patch of sky, we find more planets. Planets around red dwarfs, planets around binary stars, planets tucked into orbits that would allow liquid water on their surfaces. The more we look, the more there are. It is starting to seem like planets are the rule, not the exception. Almost every star you see at night probably has at least one world circling it. So life should be easy, right? The ingredients are there. The conditions are there. The time is there. Our galaxy alone is over 13 billion years old. Earth is only about 4.5 billion. So there were stars and planets sitting around for 8 or 9 billion years before our sun even ignited. That's plenty of time for someone else to figure out chemistry. Plenty of time for some other planet to develop microbes, fish, lizards, philosophers, radio telescopes. Billions of years of head start. Even if only 1 in a million suitable planets produces a civilization, that's still thousands of civilizations in our galaxy alone. The galaxy should be crawling with them. They should have had time to colonize the whole thing, even moving slowly. This is the argument that convinced nearly everybody. And I'll admit, when you lay it out like that, it feels airtight. You'd be a fool to bet against it. And yet, nobody is here. Nobody is called. Nobody is visited. Nobody has left a mark anywhere. We have been able to look. The sky is silent. Now, a lot of people hear that silence and shrug. They say, well, we haven't looked hard enough. We've only been listening for a few decades. We've only checked a tiny fraction of the sky. Give it time. But that excuse has a rotten foundation. Let me show you why. It is not about listening. It is about colonization. If even one civilization anywhere in this galaxy had developed the ability to travel between stars, even at a tiny fraction of the speed of light, say 1%, they could have spread across the entire Milky Way in roughly 10 million years. That sounds like a long time until you remember the galaxy is 13 billion years old. 10 million years is less than 1/10 of 1% of the galaxy's lifetime. It's nothing. It's a Tuesday afternoon in the life of the galaxy. If anyone had started colonizing even once at any point in the last several billion years, they'd be everywhere by now. Not almost everywhere, everywhere. And everywhere includes here. They are not here. So the real question is not, is there life out there? The real question is, what is stopping it? And this is where the physics starts to bite. Not gently, not with a polite suggestion. It bites hard, and it does not let go. Let me take you through the walls. Not metaphorical walls. Actual physical walls that the universe puts between any 2 points in space, any 2 moments in time, any 2 civilizations that might want to reach each other. The first wall is the speed of light. And people misunderstand this so badly it makes me want to scream. They think the speed of light is fast, 186,000 miles per second. It is fast if you're trying to get from New York to Los Angeles. Light can circle the Earth 7.5 times in 1 second. Wonderful, impressive, completely irrelevant once you step off this planet. The nearest star to our sun is Proxima Centauri, about 4.25 light years away. Let me make that real for you. If you shrunk the sun down to the size of a grapefruit and set it on your kitchen table, and you shrunk the Earth down proportionally, the Earth would be a grain of sand about 15 feet away. Fine. Now where's Proxima Centauri in this model? It's another grapefruit, sitting in a city about 4,000 miles from your kitchen. That's the nearest star, the one right next door, and the galaxy has 300 billion of these grapefruits spread across a volume so vast that if you could somehow see them all at once, the gaps between them would make you dizzy. A spaceship traveling at the speed of light itself, which is physically impossible for anything with mass, would take 4 years and change to reach Proxima Centauri. The galaxy is 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years away. 2.5 million years of travel at the fastest speed the universe permits. That is not a distance you can overcome with ambition. That is a wall. And you cannot reach light speed. Einstein showed us this, and it is not a suggestion. Nothing with mass can travel at the speed of light. As you push something closer to that speed, its energy requirement does not just grow. It goes to infinity. Not gets very large, infinity. You would need more energy than exists in the entire observable universe to push a single grain of sand to light speed. This is not a technical limitation awaiting a clever engineer. This is the geometry of space-time itself, telling you no, the speed limit is woven into the structure of reality, the same way the ratio of a circle's circumference to its diameter is pi. You do not negotiate with geometry. Fine, people say. Forget light speed. What about something more modest? 1% of light speed. That's still fast. About 6.7 million miles per hour. At that speed, reaching the nearest star takes 425 years. Crossing the galaxy takes 10 million years. Reaching Andromeda takes 250 million years. And every single mile of that journey is through hard vacuum, cosmic radiation, micrometeorites, and the absolute indifference of empty space. There are no pit stops, no supply depots, no friendly harbors, just nothing, stretching in every direction, for centuries. That brings us to the second wall, and I want you to really sit with the numbers here because this is the one nobody wants to talk about, energy. To accelerate a modest spacecraft, let's say something the mass of a school bus, to just 1% of the speed of light, you need energy roughly equivalent to the entire annual energy output of a small nation. All of it, converted perfectly into thrust, with no waste, which is of course impossible because thermodynamics says every process wastes something, and that only gets you moving. You need the same energy again to slow down at the other end, unless you plan to shoot past your destination at 6.7 million miles per hour, which rather defeats the purpose. If you want to send actual colonists with food, water, air recycling, radiation shielding, medical equipment, seeds, tools, and everything needed to keep fragile biological creatures alive for 400 years in a metal can, your ship gets much heavier. And the rocket equation does not forgive extra weight. The more mass you carry, the more fuel you need. The more fuel you carry, the more mass you have. It spirals. The numbers become genuinely obscene. For a serious colony ship, you might need energy equivalent to a significant fraction of our sun's total yearly output. Not for a fleet of ships. For one, this is not me being a pessimist. This is the second law of thermodynamics, and I have never seen it lose an argument. Every engine wastes heat, every reaction has inefficiencies, every fuel has limits, and space gives you nothing for free. There are no currents to ride, no winds to catch, no roads to follow. It is the emptiest emptiness imaginable, and crossing it demands more than any civilization may ever be able to produce. The third wall is time, and it may be the cruelest of all, even if you somehow solve the energy problem. Even if you build a ship that reaches 1% of light speed, even if you crack hibernation or generation ships, or send self-replicating machines instead of people, the communication delay murders any hope of coordination. Here is how it works. You arrive at a star system 40 light years away. You land, you set up your colony, you send a message home, we made it, the planet is habitable, send more colonists. That message, traveling at the absolute maximum speed the laws of physics allow, takes 40 years to arrive on Earth. Earth sends a reply, wonderful news, we'll launch the next fleet soon. That reply takes another 40 years to reach you. 80 years for one exchange. One question, one answer, 80 years. Think about what 80 years means. When you sent the message, you were a young pioneer. When the answer arrives, you're dead. Your children might still be alive. They'll hear a voice from a world they've never seen, responding to a question asked by a parent they barely remember. Now extend this. A colony 100 light years away has a 200-year round trip for messages. A colony across the galaxy has a round trip measured in tens of thousands of years. Languages change in that time, governments rise and collapse, entire cultures are born and forgotten. By the time your message arrives, the civilization that sent it may no longer exist. You cannot build an empire on those timescales. You cannot share technology. You cannot coordinate defense against a threat. You cannot maintain a common culture. Each colony becomes an island the instant it launches, cut off forever, drifting in the dark. The speed of light doesn't just limit how fast you travel. It limits how fast you can think together, plan together, remain one people. It shreds the very idea of a connected galactic civilization into tiny, disconnected fragments, each as alone as if the others never existed. And there is a subtlety people miss when they talk about radio signals and listening for alien broadcasts. A radio signal obeys something called the inverse square law. Its strength drops with the square of the distance. A signal that is perfectly clear at 1 light year is only 1/4 as strong at 2 light years. At 10 light years, it's 100th. At 1,000 light years, it's 1 millionth. By the time it has crossed any significant fraction of the galaxy, it is weaker than the background hiss of the cosmos itself. It doesn't just get quiet. It vanishes into the noise, indistinguishable from the random crackle of a universe full of hot gas and spinning pulsars and exploding stars. You could have a civilization screaming at the top of its lungs a few thousand light years away, and we would never hear it. Not because we're not listening carefully enough, because physics has erased the message before it arrived. So even communication without travel, just sending a hello across the void, runs into walls that may be insurmountable like galactic scales. The universe does not just make it hard to travel, it makes it hard to whisper. 3 walls: speed, energy, and time, each one devastating alone. Together they form a cage. The universe built this cage and put every intelligent species inside its own little cell, separated by gulfs of space, so enormous that crossing them may be permanently, physically impossible. But there is something worse than the cage. The cage is getting bigger. The universe is expanding, and not just expanding, but accelerating. Every distant galaxy is moving away from us, and the farther away it is, the faster it recedes. Galaxies beyond a certain distance are already moving away faster than the speed of light, which means their light will never reach us, no matter how long we wait. The observable universe, the part we can even in principle see or contact, is shrinking, not in absolute size, but in terms of what is reachable. Galaxies that are visible today will eventually redshift into invisibility, sliding beyond our cosmic horizon forever. The universe is not just big, it is actively pulling itself apart, and the islands of matter within it are drifting further and further from each other with every passing moment. And on top of all this, the cage is falling apart from the inside. The second law of thermodynamics tells us entropy always increases in a closed system, and the universe is the biggest closed system there is. Stars burn through their hydrogen and die. Galaxies exhaust their gas reserves and stop making new stars. Energy disperses. Structures dissolve. There is a clock running on everything, and it ticks in only one direction. Our sun has about 5 billion years of fuel left. That sounds comfortable until you remember it took life on Earth about 4 billion years to go from simple chemistry to someone who could have this conversation. The margin is thinner than it looks, and we had it easy. A stable star, a calm orbit, a magnetic field to shield us from radiation, a large moon to stabilize our axial tilt, a Jupiter-sized planet further out sweeping away the worst of the asteroid traffic. How many of those conditions are common, we do not know. But each one that is rare makes the odds worse. The broader picture is bleaker still. The peak of star formation in the universe happened roughly 10 billion years ago. We are past the prime. The universe is in its autumn. New stars are still being born, but the rate is declining and will continue to decline. In a few trillion years, the last star will gutter out. After that, it is black holes slowly evaporating by hawking radiation over timescales, so immense they make the current age of the universe look like a single heartbeat. And then nothing. A thin, cold dust of particles drifting apart forever in perfect darkness. No stars, no warmth, no chemistry complex enough to produce anything interesting. That is not poetry. That is where the second law of thermodynamics leads, inevitably. Now, I want you to sit with something uncomfortable. We know exactly one example of life arising from non-life. One right here, and we still do not understand how it happened. We know the rough outlines. We know which molecules were probably involved. We have plausible environments, undersea vents, warm little ponds, mineral surfaces that might catalyze the right reactions. But the specific step from ordinary chemistry to a self-replicating system, something that copies itself with occasional errors, so natural selection can begin operating, that step remains profoundly mysterious. We have never reproduced it in a laboratory, not for lack of trying. Smart people have worked on this for decades, and the best we've managed is to produce some of the building blocks under plausible early Earth conditions. The building blocks, not the building. It's as if you showed someone a pile of bricks and said, "See, making a cathedral is easy." No, making bricks is easy. Making a cathedral requires something else entirely, and we do not know what that something else is. So that step might be trivially easy. It might happen on every wet rock in the galaxy within a few 100 million years. Or it might be the single most improbable event in the history of the cosmos. An event so rare that in 200 billion trillion rolls of the dice it came up exactly once. We do not know which. And that ignorance is not a footnote. It is the entire question. If life arises easily, then where is everybody? If it arises easily, but intelligence is the bottleneck, that is its own horror. Look at our own planet's history. Single-celled organisms dominated Earth for roughly 2 billion years before anything multicellular appeared. 2 billion years of bacteria and nothing else. Complex life is not an automatic consequence of simple life. It may be a freak accident that required very specific conditions to occur at all. Or perhaps the filter comes later. Maybe intelligent species arise regularly on planets across the galaxy, but they destroy themselves before they ever leave their home world. They split the atom and use it on each other. They foul their atmosphere with the byproducts of their own industry. They exhaust their resources fighting over territory, over ideology, over which group gets to control the last reserves of whatever keeps the lights on. Maybe intelligence is not a survival advantage at all. Maybe it is a brief bright flash, like a match struck in the dark, that burns itself out before it can ignite anything lasting. We have no way to know from the outside whether our species is the exception or the rule. All we have is the silence, and the silence does not explain itself. Whatever the answer, the silence says almost nothing makes it all the way through. Almost nothing gets to the point of looking up and asking the question we are asking right now. Let me bring it together. You have a universe with 200 billion trillion stars. What was saying the enormous, gorgeous, overwhelming in scale, and every single one of those stars is imprisoned by distance. The gaps between them are so vast that even light, the fastest thing that exists, takes years or centuries or millennia to cross them. The energy required to bridge those gaps is beyond any plausible technology. The time delays shatter any possibility of connection. The universe itself is cooling, dimming, slowly dying, and the one process we know of that creates the kind of beings who could even attempt the crossing, that process may be so rare it has occurred only once. Big numbers created the expectation. Physics destroyed it. The universe is not hostile. Now, hostile would imply it cares. The universe is indifferent. It built a playground so large that nobody can reach the far end, lit it with stars that will all eventually go dark, and filled the space between with distances so vast that even light crawls like an ant crossing a continent. People don't like this conclusion. I understand that. Something in us wants company in the dark. We want the universe to be friendly, to be full of neighbors, to care about us on a scale larger than one small world, orbiting one ordinary star. But physics does not care what we want. Physics tells us what is. And what is, as far as anyone can determine, is a cosmos of staggering beauty and staggering emptiness. Now, there is another way to see it, and I think this other way is more interesting than despair. If we are alone, then what is happening on this planet right now is not ordinary. It is not a thing that happens on billions of worlds. It is rare, possibly unique in the entire observable universe. This particular collection of atoms, on this particular rock, assembled into this particular pattern, Maybe the only time in 13.8 billion years that matter has looked at itself and understood what it was seeing. The only time the laws of physics produced something that could discover the laws of physics. If that's true, the weight of it is extraordinary. Not in some mystical sense. I'm a physicist, not a priest. In a practical sense. If nobody else is doing science anywhere, if nobody else is asking questions, building telescopes, puzzling over equations, arguing about what the data means, then the curiosity sitting inside your skull right now may be the rarest phenomenon in the universe. Rarer than diamonds, rarer than gold, rarer than any element forged in any supernova that ever erupted, a piece of the cosmos that wonders about the cosmos, and there may be no other piece like it, anywhere, ever. You cannot send a message to another star system and have someone answer. The speed of light says no. Thermodynamics says no. The vast cold architecture of space-time says no. But you can look through a telescope. You can split a beam of light with a prism and read the chemical fingerprints of a star 1,000 light years away. You can trace the curvature of space-time around a black hole you will never visit. You can work out the equations that govern how the whole extraordinary machine runs, from the smallest particle to the largest supercluster. You can understand it, even if you can never reach it. That may be all there is. And if you sit quietly with that thought for long enough, you might find that it is enough. Tell me, if you had to stake your life on one honest answer, alone or not alone, which way would you bet? Do not give me the noble answer. Give me the one that actually keeps you awake at night.